Harry Bishop has been an avid user of Mathematica since 1996. He has used it for computation, string searching, interfacing with databases, and data synthesizing, including import-export translations. In November 2006, he co-founded the Washington, D.C. area Mathematica Special Interest Group. He enjoys its monthly meetings that show the varied mathematical interests of its members. Harry will now use Mathematica to learn about quaternions and to validate the relations between their entities. His title is Quaternions, What They Are and Applications. Take it away, Harry.
Thank you. My introduction to quaternions came from computer graphics, and in a textbook on the subject, they went into quaternions as being the method for doing three-dimensional rotations, and started off with four-dimensional matrices, and basically didn't explain a lot, just said, here's how you do it. And so I kind of lost interest in the subject until recently I ran across Norman Wildberger's course on quaternions that followed up from his course on what he called dihedrons. Dihedrons were two by two complex matrices that he used to show the different formations of complex numbers. And then he also went into how you could set up quaternions with these two by two matrices. Some people may have heard of Pauli matrices that are used in a different venue. And it's a different set of matrices that form the basis for quaternions. And because it was set up as a two by two, and I wanted to learn how this process worked, I thought, well, I'll just use Mathematica and I'll follow along with the course and I'll develop the theory and also, well, not so much the theory, but just the application and see how quaternions really group together. So quaternions, as I found out, was based on 8 element subset of 1 ijk minus 1 minus I minus j minus k, and that they form a group. And you can enter the negative of the identity element, and therefore you can relate that to I squared, j squared, k squared, just as Hamilton did. And that all of a sudden looks like it's growing complex numbers. Also, Hamilton put in the requirement that ijk be the -1. And if you take this and form it as Wildberger did, you set E equal to the identity element, identity matrix 2 by 2, I equal to the matrix as shown here, J the matrix 0, 1, minus 1, 0, and then K equal to 0, I, 0. Using Mathematica, you can definitely, you can identify the bar over these elements as the negative of I, J, K, and E. And what I used here was the special characters script for the E, I, J, and K so they wouldn't interfere with any other variables. Interesting side story about this is that people are now complaining in computer graphics that they're using quaternions, but they don't understand them and they don't see a need for them. As just a backward look at the subject, the reason that Hamilton developed quaternions was because he wanted to do rotations of three-dimensional vectors, and he found that he needed a fourth dimension to make that all work out properly. I also learned from a separate little video that when Apollo, I think it was Apollo 11, was circling around the moon and trying to keep track of the command module, the gyros are programmed with Euler angles, which mean they're 3 independently rotating gimbals. However, because of computer software, you have to put a prioritization on which gimbal rotates before the next gimbal before the inside gimbals. So if you get two inside gimbals lining up, then you can get what's called gimbal lock, and you can't unlock them because there's no fourth element to independently restore their or reset their offsets. And so the guy flying around in the command command module was trying to keep track of the lunar orbiter, and he kept complaining that he was getting close to his gimbal lock position. And gee whiz, it sure would be nice if he had a fourth gimbal. So that fourth dimension is what Hamilton found you needed. Also using Mathematica, you can show that these relationships hold, that E bar times E bar equals E, and these other relationships, as I'm showing them here, they're all in an AND statement, and so that you can just basically execute and find out that, yeah, as these matrices are set up, all these relationships that Hamilton required are true. So my approach to this was to fall back on the object-oriented way that I did Mathematica earlier with some other notebooks. And that was to construct a quaternion as an independent head. In other words, undefined, but useful as a head element. And so I use this construction make 3 ellipses Q, as I've used in the past for make other objects that will only be defined through their application, not through what they mean, because they mean what it is, they are what they are. Okay. So quaternions in this construction were made up of 4 element n tuples. And I use T, X, Y, and Z as the 4 elements to describe the 4 dimensions for a quaternion. And so if I use 4 real numbers in this 4 tuple, then I can build any quaternion as defined. You then use this construct in Mathematica called up values, where you can take a head as defined, and then you can identify what operations apply to that head, and you can pick out various elements within the construct to identify separately. So for instance, if I want to define a quaternion as a 1 real number and a 3 tuple list, then it will go ahead and separate the list and then make a quaternion for me in the usual way. If I want a pure quaternion, which is basically the 4th dimension is 0, then you just specify that you want the pure quaternion as V. So V times V operated on a quaternion then gives you the pure quaternion. T then would give you the real number. And as I've specified here, you don't want a scalar. What you want is T times the identity matrix, because remember, the basis of all these quaternions are matrices and not real numbers. So Q times a pure quaternion of 3 n tuples then gives you the 0 for the real part. The X, Y, and Z, they're separately and called a pure quaternion because they all belong to these imaginary axes. To go along with the fact that the bases are matrices, then I defined MQ, which means the matrix equivalent of a quaternion is then the sum of each of the real values times their matrix elements, matrix bases. Okay, so as it turns out, T, E, X, I, Y, J, and Z, K summed all give you a 2x2 matrix, complex. And then if I ask for it, I could define the up values as a list, and it will show me what Mathematica is doing with those definitions. The interesting thing about this is that, and I'll say this early, Mathematica has a package called Quaternions. And if I look at the Mathematica package, it basically says, here's a complete package of quaternions. It's basically meant to be used with real numbers and only has limited support for symbolics. Well, since I'm trying to learn about quaternions, I'm really not interested in the actual numerical values. So I decided to stay with this approach of just using symbolics, although I did modify my definitions so that when I put in real numbers, then of course it would give me the right response. And the reason that that may sound a little convoluted is the fact that the way Mathematica does symbolics, it never knows whether a symbolic variable is complex in itself or whether it's just a real number. And so you have to make your definitions so that it gives you what you think you're supposed to get for symbolics. So anyway, this whole thing will be done in symbolics, but I do want to make sure that it will also apply to real numbers because I want to use it later for applications. So if we look here at what a quaternion is on construction, Q of the values 1, 2, 3, 4, and then I can ask for what is the pure quaternion, and you see that the first value is 0. I can look at the matrix form, and the matrix form is still a 2 by 2 matrix, but it also has specific complex entries. The nice thing about doing it this way is the fact that Mathematica has a well-defined complex variable arithmetic, and so it treats everything correctly. And also you'll see that I use the matrix form of operations, and therefore the Mathematica matrix operations are already well-defined, and so it follows along nicely. If I look at the matrix form for just the value Q1, 0, 0, 0, I get the identity matrix as you would expect, because that's the basis element. And if I look at the matrix for a quaternion of all zeros, then of course I should get the 0 matrix, and I do. So then the next thing is, with this quaternion definition, then what kind of operations can we define for it? And there's a number of them. And so if you were to follow along with the Weilberger course on YouTube called Quaternions, that's the order in which I take things along here, although I did add a few things to match up with the Mathematica package of quaternions. So the first thing we want to do is we want to look at how do we add 2 quaternions. So 2 quaternions, as you might expect, we just add the elements term by term. Since they're a matrix, then that means the matrix version also just adds term by term. The difficulty comes in, well, what if I want to add a complex number with a quaternion? Well, since a complex number is a quaternion, I definitely want that to turn out to be a quaternion. And so that also is part of the definition here. I use the question mark number Q because the number A could be a real number or it could be a complex number. And as it turns out, when I'm using symbolics and I'm using number arithmetic, then I need to get Mathematica to register that the symbolics aren't some other form of complex number because I'm treating them all as real numbers, and then the complex just comes out of the quaternion definition. So this is the way that it works out. And then we get term by term addition. So in this regard, I also wanted to investigate, could I use subscripts as I might do in a typical fashion? So I made one quaternion with T1, T sub 1, X sub 1, Y sub 1, Z sub 1, and Q2 respectively. And then I wanted to see if I could add the two together, and then Mathematica would track. And of course it does. So Q1 plus Q2 then equals term by term, even including symbolics and subscripts. So that's nice. That means I can go through and sort of keep things in a consistent fashion. There is a liberal use of simplify, complex expand, and so forth, because the final form needs to be the same for Mathematica to register that they're the same. But in doing the complex arithmetic with symbolics, you sometimes have to force the issue that, yes, keep reducing until you get the format that will apply. Another interesting thing that I found was that if I want to show the matrix addition format, I can take the matrix of Q1, the matrix of Q2, and add those two. Using table form, I get the table spacing. I can apply that to matrix form, and therefore I get a nice output here that shows how they add and keeps track of everything in the complex version. So I thought that was rather nice. Multiplication therefore is the second operation we want to define. And in multiplication, since a complex number is a quaternion, the first thing I need to do is define complex numbers or real numbers times a quaternion that ends up giving me a quaternion. And I need to do that in a commutative fashion, as we would expect, because a scalar times a quaternion should still be the same quaternion, whether I multiply prefix or postfix. And then I wanted to find the multiplication of two quaternions. And in this regard, since they are matrices, it was just easy to show that the two matrices are matrix multiplication. The interesting thing here is that I put the quaternion with T, X, Y, and Z in the tuple before the A, B, C, and D, because otherwise I found symbolically it would not understand the non-commutativity, and it would always reverse them to be the order that is lexicographical. So by putting the definition in the up value as reversed, then it maintains the non-commutativity of the symbolic matrices. So here's an example of a complex expression where I have a complex number plus a quaternion minus a scalar times a quaternion. And of course, it gives me what I would expect for the quaternion that results, Q2 minus 700. And I also compared that over here with the version for Mathematica, and I get the same result. In matrix form, we can see what multiplication amounts to. And note that I use the dot here for multiplication of two quaternions, because that preserves the matrix operation of multiplication. So on the left is a product of two quaternions with their subscripts, and on the right is then the equivalent matrices with the subscripts and how they multiply together. If I do this in the quaternion package and multiply, it just sort of gives me all of the resulting quaternion with all the real numbers, but it doesn't show me how the matrix actually multiplies them together. And the matrix definition is going to turn out to be useful later on, so it's nice that we follow this convention. Also, since it's 2 by 2 matrices are really easy to work with. Okay. In addition to doing a quaternion as an equivalent matrix, complex matrix, then I also want to be able to invert back. So given a complex matrix of a quaternion, I want to be able to generate, well, what was the quaternion form? So I have this invert function, which does that for a symbolic quaternion. And then it turns out that I need this complex parts of a complex symbolic representation using this function with refine to identify the real and complex elements. when I identify the values as reals, not complex symbolically. And so that becomes a different module than if I want to invert a quaternion of real values, then I need to use this simpler form, just finding the real and imaginary parts. Now it's easy to find the inversion because if we look at the matrix representation of a quaternion, the format is always the same, T plus IX in the first element, T minus IX in the opposite diagonal, and then you see the Y plus IZ and the minus Y plus IZ. So this form is always the same for a quaternion. That means that you can take the first element, pull out T and the first two elements of the n tuple, and then you can look at the first row, second element to pull out the third and fourth element of the tuple for the quaternion. And you might say, well, what if that's not correct? Well, we're going to show later how we evaluate whether that is a quaternion, just given a complex matrix. So doing the inversion, if I invert a matrix, a complex matrix, and I do the inversion, and I take the rest of the result being the n tuple, then I'll get the pure quaternion part. And I can evaluate whether the matrix is a quaternion by looking to see whether I invert it, put it into a quaternion, take the matrix, whether that gives me back the original matrix. If it doesn't, then it obviously isn't a quaternion. So there's a pattern, there's a form that you can test. And then I show the examples here, testing a numbered matrix. Here's the matrix form of Q3, 2, 4, 6, and then I convert that to get the n tuple back. And I can also put in the 0 quaternion, and yes, it gives me back the 0 n tuple. So it does work. So I can test if a matrix is equivalent to a quaternion 2 by 2, and does this Q of T, X, Y, and Z. If I take the matrix form and then ask whether that matrix is a quaternion, I get back true. I can show that quaternion 1 times quaternion 2 is equivalent to a quaternion made up of a scalar and a vector portion. Now, if you take the two n tuples as identified by this format here of T times the identity matrix plus Q times I times Y times J times plus Z times K, and you take that as an element, multiply it by itself, knowing the rules of IJK multiplication, then it turns out that when you gather all the terms, that's equivalent to T1 plus T2 as the first term. Let me see. Where am I? Excuse me. That's equivalent to T1, T2 minus the dot product of the pure quaternion part plus T times V2 plus T2 times V1 plus what's equivalent to the cross product of the pure quaternion part. It was this revelation that excited a lot of people about why do we have to mess around with quaternions? We've got the dot product, we've got the cross product, and then it turns out that Willard Gibbs and Oliver Heaviside decided we've got the dot product and the cross product in three-dimensional form. That's all we need. Let's go off and do electromagnetism and everything else, and we don't need quaternions. They actually won the order of the day when you realize that Hamilton had an ally by the name of Maxwell, who cited that he liked quaternions and using it with Maxwell's equations, but everybody decided to pick up on dot products and cross products, and so that's why it's taught today in our vector analysis. Anyway, can we show with what we've done that Q1 times Q2 gives us this equivalent result? And I show you here with Q1 being the Q with T1, T2, T1, X1, Y1, and Z1. I take the pure quaternion part, call that V of Q1, similarly V of Q2. I find the T scalar part as T1, T2 minus the dot product of those two pure quaternions. I take the vector part as T1 VQ2 plus T2 VQ1, and I actually take the cross product of VQ1 and VQ2, cross being defined as a Mathematica function. And I form what's called Q form as the quaternion made up of T scalar plus the Q vector part. And then I find its matrix form and complex expand it. And what I'm showing here is that here's the result of the pure quaternion, the second pure quaternion. Here's the product of T1, T2 and the dot product. Here is the term with the cross product and the matrix, the Q form of putting all those into the n tuple. And I take the matrix equivalent. There's the matrix equivalent. And now I just take Q1 dot Q2 as their matrix because it's matrix multiplication. And all of these turn out to be true once I do the complex expands. And so I can go through here purely symbolically and prove the result. I can also look at the table form of inverting that Q form, and I can see each of the individual elements here as lined up, so I don't have to try and pick them out of this big expansion. So I can also show the uniqueness of Q with any matrix of Q and through the inverse. So I can show that if I take this matrix, if I take this quaternion of QT, QI, QJ, and QK with these terms, then I can ask for the matrix equivalent of that. And I can ask, is that equal to the product again? So basically I took the product, I formed the matrix, now I'm taking the matrix, I'm inverting it, and I see whether it gives me back the matrix, and it's true. We can ask for the conjugate relationship of a quaternion, or a conjugate of a quaternion, which is the same as the scalar part, which is considered the real part, but take the negative vector part, okay, since the vector part is complex. So the conjugate is defined as Q of T, but take minus X, minus Y, and minus Z in the n tuple. And so that value is then defined, and then we can look at what the equivalent matrix form is. And as you might expect, you get T minus IX instead of plus, and you get minus Y, minus IZ instead of plus IZ, okay, across the first row. Given this matrix representation, you can look at the potential for what's the conjugate transpose of a complex matrix, which we have here. And that's obtained by taking the transpose of the matrix and then taking the complex conjugate of each entry. So I define that conjugate transpose as A asterisk. And it's interesting, but Mathematica lets me define the symbol A superscript star to be the value that I want. And then we can show that the complex, well, we know that the complex square matrix is normal because it commutes with its conjugate transpose, okay? So we can show that this is true. So the first thing I do is I take a quaternion, find its matrix equivalent, assign that to A, and then I can define the conjugate transpose of the matrix A as this matrix here, as we've already shown, by taking the transpose and then the conjugate of the individual elements. And then I can show that A times A star is equivalent to A star times A, meaning that the matrix is normal, and it's true. The value of being normal is really nice because a normal matrix can always be diagonalized. And so that will come into play later when we want to ask about, well, what's the function of a quaternion? So we can use that property. We can also show that a quaternion times its conjugate is commutes with its conjugate and times the quaternion. So still staying in symbolic form, we show that that's true. We can also show that the matrix conjugate transpose is equal to the matrix of the conjugate of the quaternion. So all these relationships turn out to be true. Okay. The interesting thing is there's a function in Mathematica called conjugate transpose A. So I thought, well, I'll just throw A in there and see if it gives me the same result. And what it sent back was, yeah, you asked for the conjugate of all these things. But since they're symbolics, once again, Mathematica has difficulty with that because it doesn't know what these things represent. And I tried various things like identifying the elements as real and various other methodology, but I could not get it to work. So staying with my own definitions here allowed me to continue to proceed instead of relying on the Mathematica function. We can also show that the conjugate of a product of quaternions is equal to the product of their conjugates. So I can show that a product is Q1, Q2 using the super subscripts. I can identify each of the elements then from the inversion of that quaternion. I can then put those elements back into the conjugate of that product, and I can show that that's equal to the product of the conjugates of individual quaternions. So we show that that's true. Now we might ask, well, is that, since I did this all in matrix representation, is the conjugate of that product still a quaternion? So I go back to Q, capital Q, and I get true. So everything works out. There's a term that Weilberger uses. I was not familiar with it, but it's called quadrants. And quadrants is defined to be the square of what we normally call the absolute value of a complex variable. Okay, so in other words, the quadrants is defined to be the square of and sum of each of the individual elements. So t squared plus x squared plus y squared plus z squared, when the quaternion is defined through t and comma x comma y comma z. It turns out that the quadrants is also equal to a quaternion times its conjugate. It's also, the quadrants is also equal to the matrix representation if you take the determinant. So all three of these are the same. So we can identify a unit quaternion then as a quaternion that's divided by its quadrants. Or a unit quaternion is then the quadrants of a quaternion that is whose quadrants is 1. A unit quaternion of the matrix then means that the determinant of the matrix is 1 when the matrix represents a quaternion. So we can show all these identities as true, as the quadrants of Q of T, comma X, comma Y, comma Z is equal to the determinant of the matrix representation of that quaternion. We can show that the matrix of a quaternion whose only element is the quadrants, in other words, the real part, is equal to the quaternion times its conjugate, which is also the commuting conjugate times the quaternion. So I can show that that matrix also works out. This was a neat little statement that I found, Euler's four-square identity. And since this quadrant is the sum of four squared elements, so Euler's four-square identity says that the product of two numbers, each of which is a square of sum of four squares, is itself a sum of four squares. And Euler wrote about this identity in a letter dated May 4th, 1748 to Goldbach. Interesting things that people discover, and they just write in a letter, and here it is, guys. Anyway, so we can show that that's true for quaternions by showing that the quadrants of a product is equal to the product of the quadrants of each quaternion individually. So, and I show that that's true, using the definitions of Q1 and Q2 that we've been using all along. The package of the quaternion package that Mathematica has goes into a couple of other operations called the sign and the adjusted sign. So I just threw them in here after I after I defined what the inverse of a quaternion is. And the nice thing about this approach to quaternions is that now we have inverses. Because we have a matrix representation, we can identify, and we have conjugate times a quaternion. We can use the quadrants feature then to identify an inverse. So identify the inverse of a quaternion as its conjugate divided by its quadrants. And you'll see that this turns out to be, in fact, the inverse. I'm not going to go through the sign and the adjusted sign. I define the absolute value of a quaternion then as the square root of the quadrants. And since it's a square, it's a sum of squares of real numbers, then it works out that it's positive. So the inverse of a quaternion turns out to be the conjugate divided by its quadrants. And then if I multiply this conjugate times the conjugate of a quaternion times a quaternion, I get the quadrants. So if I divide by the quadrants, then I should have the identity element E. And this shows that that's in point of fact. Okay, so Q, I'm at my 38-minute point, so I'm almost done here. So, and I can do the same thing with Q times its conjugate, and therefore I also get the identity element E, which is, if you'll recall, the identity is the basis element, and that is the equivalent to 1. So all these just show that the same is true. So we can test that a quaternion is a unit quaternion. We can test a matrix of a unit quaternion is a unit quaternion. We can show that the quadrants is 1, and therefore we can show that the inverse of a unit quaternion is its conjugate. So I defined a unit quaternion with cosine theta as the first element, 0 for x, sine of theta for y, and 0 for z. And I can show that this is a unit quaternion. It's true because its quadrants turns out to be 1. And the matrix equivalent is, as we see here, which is a rotation about the x-axis. And then we can show that it's a unit quaternion and its quadrants is 1. Okay. To continue on, we can identify an inner product. Of course, the inner product normally is using the dot symbol, but we've already used that for matrix multiplication and for multiplication of quaternions. And so therefore, I just used the function inner Q applied to the quaternion of, once again, T, X, Y, and Z, and A, B, C, and D. And it turns out to be, as you would expect, the sum of the individual elements multiplied together. And I put this in angle brackets as a second definition, so I could use either forms as you might expect in a textbook. So the inner product then of Q and Q is, of course, its quadrants. Okay, and the conjugate of Q2 is in the I'm sorry. I'm identifying this Q2 bar as the conjugate of Q2, and I can show you that the matrix form turns out to be the following, which shows us that the inner product of Q1 and Q2 is 1/2 the trace of the matrix multiplication of matrix representation of Q1 and matrix multiplication of Q2. So this is another result. So those turn out to be true. So it's, instead of messing with inner Q all the time, I can just take 1/2 the trace of the matrix multiplications. If I'm doing a quaternion operation and I end up with a matrix, then might as well just use the matrix in its present form instead of trying to revert it back again. So all these turn out to be true. So I can show that the inner product of Q1 with a generic quaternion and Q2 with that same generic quaternion turns out to be the quadrants of that generic quaternion times the inner product of Q1 and Q2. Okay, so notice the use of expand here on one side, expand on the other side, as opposed to complex expand, but that was the simplification that turned out to make these two work together. And we can look at Q1 and Q2 as the matrix representation of these. And so you can see that the matrix versions after, the inversions after the matrix multiplications also turn out to be the same Q. So in other words, the quadrants of Q, when it's part of the multiplication and then the inner product, turns out to be just the scalar part of Q. Okay, not the quadrants of Q, I'm sorry. So then finally, we can look at the extension of quaternions in a complex form. So a lot of people like to rely on Euler's formula for a complex number, but you have to be careful. So Euler's formula, just to remind everybody, was take a complex number and it can be represented as the absolute value times e to the I theta for a normal complex number. I could take a quaternion and I could say, well, let's do the same thing. Let's just take e to the representation of this complex number in terms of its I, j, k elements. Unfortunately, when you do that, you end up with the product of 4 exponentials. And as we know, the exponentials commute, but the quaternion doesn't. All right, so you can't really use that format. But what we can do is we can identify the quaternion as a real part and a pure quaternion part. If we do that, then we can end up keeping the I, j, and k with normalized elements within the pure quaternion part. And then the quadrants turns out to be t squared plus the pure quaternion quadrants. And therefore, we can end up with a format that looks like, the absolute value of Q, we can take cosine of the identity element plus the sine of theta times the sum of the pure quaternion part. Since the product of the pure quaternion part squared is -1, as you would expect for a complex variable I, then Euler's formula continues to work in this format. And then this allows us to do a number of things with regard to functions and other representations. The most important being, why do people use quaternions in the first place? And I'll have to save that for the next part of this, where I show that the rotation of a pure vector, of a three-dimensional vector, or a pure quaternion is equivalent to a quaternion times the pure quaternion times the conjugate of the original quaternion. So if the axis of rotation is a quaternion in four-dimensional space, and the pure quaternion is in three-dimensional space, then the four-dimensional quaternion times, as long as it's a unit quaternion, times a three-dimensional vector times the conjugate of the unit quaternion turns out to be the rotation of the three-dimensional vector, only at twice the angle that separates the four-dimensional quaternion from the three-dimensional vector. I'll explain more of that in the next part. And now I'll open it up to questions.